Hi, I'm Meta Spencer, and today we're going to talk about brightening the clouds. It may have not have occurred to you as something worth trying, but we're going to brighten some clouds today. And I have three very important climatologists with me who will certainly have things to say to each other, although I probably won't be able to follow all the technical details, but I'll ask all the right questions for people like myself who don't know enough. I'm going to introduce, I would say, our featured speaker in a way today, because this is the person whose innovation we will be most considering, and that is Professor Stephen Salter, who is who's an emeritus professor of engineering at the University of Edinburgh. And I guess, are you still in Milan, Peter?
Turin.
Okay, not Milan, but Turin or someplace.
Yeah.
And he's been in northern Italy a lot lately, I think, haven't you? Anyway, he normally is based in England, I think, but is teaching for a while in Italy. And this is Professor Peter Wadhams, who is, of course, an expert on the Arctic. And I think his concern will be, what will this cloud brightening do for Arctic sea ice? And then here in Canada with me, just a hop, skip, and jump down the road to Ottawa, is Paul Beckwith, who is also a climatologist. So, hi, Paul. How are you today?
Thanks. I'm good. Thank you.
Good. Okay. What we want to talk about is how to restrain global warming. And Stephen Salter, if you don't mind leading us off, I will ask you to please give us your pitch. If you're trying to find somebody to fund your project, what would you tell them?
Okay, well, the beginning of the story is from a chap called Sean Toomey, who was interested in clouds, and he flew over them and measured the amount of sunlight coming down from above and the amount of sunlight that was being reflected back up from the clouds, which was an interesting thing to do. And he worked out that the reflectivity depends on the size distribution of the drops in the cloud. And if you keep the water the same, but you have a lot of small drops, you get a white cloud. And if you have the same amount of water in a smaller number of bigger drops, then you get a dark cloud. And you probably heard people saying the dark storm clouds are gathering when the drops are getting big enough to fall. And you can demonstrate this with jars of glass balls, okay? And this one has got 4mm balls, and this has got 40 micron balls. And you can see there's a big difference in contrast, okay? And that's been validated. Somebody else checked it, and everybody believes it. And then a chap called John Latham, who knew about Toomey's work, realized that you might be able to use it to control climate change. And the key thing you need to know there is that clouds need to start growing, cloud drops need to start growing on a tiny little nucleus. It could be a bit of dust or maybe a bit of ice, but they need something to get started on. And there's a shortage of these over the clean air in mid-ocean. And John Latham thought that maybe if you could filter seawater and then make tiny, tiny submicron drops of it and spread them out, and they would evaporate and leave little salt crystals, and that these are absolutely perfect condensation nuclei to start new clouds growing, new clouds stop growing. And he worked out how much water you'd need to spray and was amazed at how little it was if you got the size of the drops right. And he heard that I was working on something that was a bit relevant to this and asked me if I could make the spray for him. And I have been trying to do this for quite a long time now, and we're nearly there. But the key names are Sean Toomey and John Latham. And the effect that they are exploiting is by a chap called Kohler, who worked out everything about what makes a tiny fragment in the air be able to successfully produce a new cloud drop. And it's really just adjusting the size distribution of the tiny bits that are making new clouds. Is that correct, Peter? Is that fair?
Yes, that's absolutely right. And perhaps we should just add that sadly John Latham died this year.
Yeah, just a very little while ago.
You're trying to simply reflect light back out of the, prevent it from landing on the planet. And that will do what? Why will that help?
That keeps the ice frozen. At the moment, if you have ice over the Arctic Ocean, most of it's reflected away and goes back out to space. It's ice and snow are very, very good reflectors. If that ice melts, the sea is very, very efficient at absorbing all the sun. The sea looks really black from above, and so you'll warm up. If the ice goes, then the sea will get a whole lot warmer. And it's the temperature of the sea which is allowing methane to escape. There's a lot of methane at the seabed, and if the Arctic Ocean warms at all, this can be released. And at the moment, it's bubbling up, and it's also melting in the permafrost in the land around the Arctic Ocean, and they're getting troubles with the subsidence of all the buildings that were built on permafrost. So I think there's more carbon as methane available in the Arctic than there is in the atmosphere. And in the first year of its release, it's about 200 times worse than carbon dioxide. So it's doing about a third of the warming at the moment, but it could easily take over from carbon dioxide if it starts bubbling up.
Now, why would this be more valuable in the Arctic than any place else? I would think there's not much sunlight anyway in the Arctic. And so your cloud brightening up there wouldn't be very helpful, but cloud brightening at maybe, lower latitudes would. Sorry for a dumb question, but I promised to ask really dumb ones.
Depends on the time of year. In the summer solstice, there's actually more solar energy going into the poles than into the equator. It's difficult to believe, but it's because it's coming in over 24 hours. So that instead of going into the equator for maybe 6 or 8 or 10 hours, it's coming in for 24. I have a map of that if you'd like to look at it. I'll see if I can find it.
Then I'm going to be quiet and let Peter and Paul do most of the interrogation. I've asked all the questions that have bothered me so far.
These are months through the year, June to December, and this is latitude. So that's the South Pole, that's the equator, and that's the North Pole. And you can see that in December, there's 550 watts per square meter going in to the South Pole for a short time. And in the winter, of course, there's nothing at all going in there. So there's more in this time and that time than there is in the equator. Mm-hmm. All right, this is from NASA, and you can get it from Wikipedia. Right, okay, is that pretty?
Yeah.
Yeah, so we'd only be able to do this for about a month either side of the summer solstice, but we could also do it anywhere in the current that's bringing heat into the Arctic. And this starts off down in the Gulf of Mexico, and there's the Gulf Stream and then the North Atlantic Drift, and that's bringing warm water up to the Arctic, and that will be melting the ice along with the solar input. And if we could cool that water flow, we'd be saving the ice. And we can do it anywhere along that path. The only reason for wanting to be at a high latitude is that you get your result a bit quicker. You don't have to wait for the water to move there. And also there's maybe fewer people to object if you're doing it up around Iceland. And the way we would do it is done from ships that are able to move around. So you could do it for a couple of months for the summer in the Arctic, and then you could go down further south and you could moderate hurricanes to stop terrible Category 5 hurricanes. So we've got a mobile cooling method, and we can move them very quickly if we need to.
There you go.
Okay. So Stephen, I had a question for you. Pumping seawater through nozzles so that the salt crystals go into, maybe a kilometer and a half up, right? So that it's so one could say that you're sort of like a salter, right? Doing this. Now, did you change your name, or were you born to be a salter?
The salt here. We don't. By the way, we can't pump them up. We just release them, and they get moved by turbulence.
Right.
When the wind is blowing over the sea, it produces a lot of turbulence.
Right. You do it, and you're released from the top of your towers on your ships that you're talking about. Okay, so a serious question now, aside from the joking about your last name, which I've sort of had, people have asked me, did he change his name? No. So the question I have is, with your technology, there's two big components. There's a component with the pumps and the mechanism to deliver to the salt particles to the air, and then there's the ships themselves, like a new type of ship, an autonomous ship, run by the vertical axis movement of the rotors, right? So new technologies for that. Have you considered as a first step, just working on getting a device, which would pump the salt particles, near the surface that could go on conventional ships?
Yes.
Because it seems to me, with all of the ships plying the ocean, if you had a device which is easy to use and you could train a crew member to operate it, they could run it from all of these commercial ships, depending. Now, the routes of the ship, so you could select ships that had routes where you wanted it deployed, and they don't necessarily have to run the device throughout their whole cruise. They could do it when they were in the locations that you thought were best.
Yes,
right.
We are designing all the spray equipment to go into an ISO sea container. Okay, and we can make something which is doing not the full amount of one spray vessel, but enough for you to do an experiment. The trouble is that the ship owners want to get their ship from A to B as quickly as possible. And if you said to them, can you just hang around for 10 days in the middle of this, they would not be at all pleased. Now, there might be research vessels that could do this, but I think most ordinary ships, first of all, they're all going along the same path as each other because they're just on the Great Circle routes. And they wouldn't really want to be interrupted doing what they is earning the money. But we will have this, and we could do it. Another complication is that the ships are already producing very often ship tracks, which are quite often reflecting more than we need to save the planet.
Right.
To see a ship track, which you don't see them all the time, but to see a ship track, you need a contrast change of about at least 15%. 30 would be better. And we're trying to increase reflectivity by about 2%. So the ships are making a very messy an inconvenient change to what we're trying to measure.
Right.
So you'd have to persuade the captain to switch off his engines or use a special clean fuel or something if you're going to do this.
But I think that, if you could get devices, get a shipping container is a perfect. That sounds like a perfect way, and then you can just have that could be shipped,
it would be
to any
very quick.
location.
It would be very quick, but you really want to be able to test over a wide range of different meteorological conditions. So what we'd probably do would be to have this container put on a lonely island with clean air coming in and clean air going away. And we might need to put a wind turbine in there to give it the energy. But we really need to test all the times it isn't going to work properly and all the times it's going to work very well and all the middling ones. And therefore, we want it for at least 6 months in the same place.
Right.
And no ship owner's going to say, oh, yeah, well, 6 months. No, I don't mind. They would use it for a day or two maximum, I think.
Right. Now, what's the life? What's the actual lifetime when you create these very small cloud condensation nuclei, right? And they create small droplets of the water. The water bonds to the small cloud condensation nuclei. I understand, like what sort of lifetime do you have of these? Because if they combine and coalesce, they'll form bigger drops, which can then fall. They'll dissipate, they'll spread out. Do you have a handle on
Yes,
some of those?
I can tell you exactly. It's half the mean time between rain showers. Okay, the thing that gets rid of them is that they get washed out by rain coming down or drizzle,
Right.
and they fall. If you measure this, if you calculate the velocity, they'd fall in still air. It's very, very slow,
Right.
and it's much slower than the random turbulence. And the turbulence is actually blocked near the sea surface. So if you know about random drunkard's walk, turbulence will be trying to spread them right through the different heights and sideways. And it's far more than the Stokes falling velocity.
Right.
So
And
when it rains, it's all cleaned off and you have to start all over again.
And the clouds, over the ocean, I mean, there's not huge areas of convective uplift. Like there's no topography, for example, to force air up. And so it's just cold fronts and meeting warm fronts that force the air up.
Wait a minute. No, I disagree. In the sea temperature is almost constant, but the air temperature above it varies a lot through the day. And at night time, the sea is still hot, and that's sending warm air upwards. And that's where most of the mixing is going to come. Okay.
So the clouds are mostly a kilometer or two above the surface. These are the low-level marine.
Maybe not quite that much. It varies quite a lot. I think in the Arctic, it's down to about 100 meters when there are clouds there, but it might be 1,500 in the middle of the Pacific.
Meta started us off by talking about methane and the Arctic, and we're applying that to the question of marine cloud brightening, which is a global effort that can be made anywhere at any time. But if we're thinking about how can that effort be made to have the biggest effect on the Arctic, this is an important question because people are concerned very much about the disappearance of Arctic sea ice and what can we do to bring it back. And the problem is that there isn't a good answer to that question. There isn't a simple way to bring it back.
What you need to do is to measure how fast the ice is going, and it's between 10,000 and 25,000 cubic meters a second. Okay, I always like to think in terms of seconds. And if you know the latent heat of ice, which you and I know, but maybe not everybody, that'll tell you how much heat is going into melting the ice. Okay, and you can then say how much sun is coming in for the short time we can operate, and that'll tell you what joules of energy are coming in, and then you can say how much of that do we have to not let in order to stop it melting. Now, you also probably need to know how much is coming in with warm winds and warm currents, and you're the best person in the world to say what that is. I've done some rough calculations, and it's not quite as much as the sun melting, if I'm right, but I'm not going to bet my pension that I am right. But that tells you how much you've got to reflect. And I have sent this calculation around to quite a lot of people in the climate community saying, are the assumptions that I've made about how deep the boundary layer is and how much sun's coming in and how long the drops last and that kind of stuff, would you like to change any of these numbers? And only one person did, and I have changed that assumption. I'm really saying this is the shape of how you do the calculation rather than I'm absolutely confident that I'm using the right inputs. But it gives you a number of vessels that you need to operate for 60 days to save that amount of latent heat of melting. If you can give me, I can give you the cost of that roughly. If you can say we'll estimate the cost based on the costs of corvettes built for the Royal Navy, which are built in similar sort of numbers, and that will tell you what the benefit to cost ratio is.
And it's very important as well to get this to the COP meeting so that this can, as a technique, it can be considered and something can be done about it. Some actual implementation can be started, which is very much overdue. But as well as the heat, the thermal analysis, there's the other more simple analysis, which is simply during the summer months, the sea ice has retreated, and the ocean has warmed up. And because the ocean is warming up, then the seabed is warming up, and that's the biggest threat at the moment for methane, is the fact that this warmed up seabed is causing methane to be released from the seabed, and perhaps in some dramatically disastrous way. But to deal with that requires pumping at a time when you have the capability of increasing the ice limit. So you'd want a time when the ice is retreated towards its absolute minimum, because there's plenty of open water, which is unfortunately warming up. And then you pump and you hope that the effect of the cloud brightening will then cool the region of where the ice has retreated and help the ice to advance. So this was an analysis which we did a few years ago with Latham and Gadian, and the predictions of a model were that it would work, and you wouldn't save the Arctic sea ice, but you would increase the ice limits in some fairly significant way, so that you would reduce the amount of retreat in the summer, and therefore maybe improve your chances of escaping from a major methane outbreak.
Yeah. I think the ice weight argument, the rate at which ice is actually melting, seems to be the best starting point for this. But there will be other heat inputs which we need to make measurements of, or at least be enough to do the calculation.
Yeah, I think these units being deployed also on the Pacific side, would be very important, because there's a lot of warm water from the Pacific Ocean going into the Arctic as well.
It actually goes out as well, but
yes,
the majority of it's coming in.
Yeah. What's coming in is below the surface, a few hundred meters down at least.
Well, these ships. So I don't know if Stephen's got a nice slide of the ships that would involve. I mean, I've got one, but it's in my system somewhere, because of their design is very, very nice for directing them.
I've got.
You showed me a couple of other slides, Stephen, that were of interest. Not only the ships, but also a map showing how much the Arctic would benefit compared to other parts of the planet. Can you bring up both?
I try and share screen again.
Okay.
Yeah. So Stephen, I did look through your whole presentation, the PowerPoints, and what I'm going to do is I'm going to do a video or two for my own channel on the content of your slides, to try to promote this idea a bit more, because they're very interesting.
Okay, well, I'll send you bags of stuff. This is what we need: energy in the middle of the ocean, and this sounds like sailing ships, and that is the final pinnacle of the technology of sailing ships. That's Cutty Sark, and I'd like you to think about men climbing up here in the middle of the night when this is rolling wildly to take reefs and things. They're quite fantastic. It's beautiful, but the whole shape of it is designed just to be commercially profitable. Right, that was the very first ship that we thought of, with propellers down here and these Flettner rotors acting like sails. And this is a classical picture here by a chap called Prandtl, who was one of the great hydrodynamicists. And this is showing a conventional ship here with conventional sails. Also, it's got these funny little cylinders here, which are spinning, called Flettner rotors. Okay, there's the Flettner rotoren. Okay, and Flettner worked with Prandtl, and he worked out how much force you get if this has a wind blowing on a spinning cylinder. And he converted a conventional sailing ship to having Flettner rotor propulsion, and had a race against the identical sister ship with conventional sails. He sailed from the Baltic to Edinburgh, or actually Leith, which is Edinburgh's port. And the rotor ship won, and he then sailed across the Atlantic to New York and got there very well, and everyone was very excited by this. And then he got orders to build lots of more with bigger ones. And then the 1929 Depression came along, and he only built one, and everything was forgotten. They're now fitting them again to big proper ships, and they are saving about 15% of the fuel. This was the very first one, and we had propellers here acting as turbines, and we found that they had a very big drag trying to oppose the forward motion. So these were to get the energy to spin the rotors and make the spray. And so we then went away to this idea where we have hydrofoils below the surface of the water, which are providing all the lift, like flying an airplane that are lifting it up. But we're also changing the pitch angle of the hydrofoils so that that one's coming up and this one's going down, and that one's coming down and that other one is going back, so that they're flapping alternately like that, up and down, with the port and starboard out of phase and fore and aft out of phase. And that would give you the energy that you need to make the spray. If anyone wants to look at this this is a fantastic thing of this Flettner, sorry, this hydrofoil ship. And this boat is out of the clear of the water, and it's flying on that amount of wing there under the water, a tiny little bit to steer. And this is an amazing, well worth looking at. What the present design has got this shape with the spray. We found we couldn't have a room inside the rotors for the spray release. So we got rid of one of the rotors, and we've got the spray mechanisms on a mizzen mast here, pointing horizontally out. As soon as the water comes out, it starts evaporating, and that cools the air, and so it doesn't come out horizontally. It actually slopes down because the air is dragging it down. The air can't get into the sea, so it gets blocked here, and then it spreads out like a spilt liquid, and then it gets warmed up and off it goes. And you can see these little white discs here. Those are all things that are plugged into sockets in the ship hull. And if you look at this one here, you can see all the different bits of technology for pumping and filtration and batteries and storage and control systems are plugged in, like screwing a light bulb in. And this is
I hate to be dumb, but you're going to need to work harder on my comprehension. I don't get what these three big pillars are, as opposed to the spray thing that goes sends it sideways. What
they are acting like sails.
They're acting like sails.
Yes, it's a propulsion of it's the propulsion mechanism for the ship, Meta. So they rotate, and there's a low pressure area created at the front and a higher pressure at the back, and essentially it pushes them forward. So they act as the wind going over them. It generates forward thrust.
Yeah,
most people just go to Wikipedia and look at Flettner sails, and it explains. Or some of Peter's stuff. It explains that's to push the ship forward, and it can do so. Stephen was saying that with 15% fuel savings over conventional propulsion.
But now this last slide you showed seemed to have spray coming out of these pillars too. So it can have dual use or not. One of them had spray seeming to come out of the tall red things.
The top,
yeah. But we found that there wasn't really room to make the spray mechanisms inside.
Oh.
And also we found that the spray had to come out horizontally because you didn't want birds droppings getting in. It had to change direction to come up the rotor, and it came up the top, and it wanted to change direction again, and then again to come down again because it was cold and wanting to. So it was keeping on changing direction. And every time it did this, there was more chance of drops coalescing, bumping into each other and being lost.
And condensing on the sides.
Yeah. If you can have a directly straight path with no changes of direction, you're reducing the coalescence. So that's why we wanted to move to here. And we also can have more spray release mechanisms here, and we can have little hatches over them to turn them off when we're not using them.
But I'm confused, because I would have thought you would want to be squirting things upward, not down. If you're trying to brighten the clouds, don't you want to get the particles up there where the clouds are?
You do, but you have to wait for that to be done by warm air dragging them up at nighttime. The air cools over the sea at night really very rapidly, but the sea stays warm. So overnight, the air will rise up and take them with it. If you did try and shoot them like a shotgun, the velocity would be reduced very, very quickly by the air drag. So you wouldn't be able to shoot them up. Even if you're using an anti-aircraft gun, you couldn't get stuff up.
Right.
It can only get up by the turbulence of the random motions of the air. The air
but you mentioned the idea of an aircraft. Now, what's wrong with the idea of having airplanes fly over and drop these droplets?
You could do that, and you could do it in an experiment. And that, of course, was what Toomey was doing. He was flying over them. It's actually very, very bumpy flying low over the sea. You may have noticed sometimes when you take off over land that the airplane is bumping a lot, and then suddenly gets calm just as you go through the clouds. Usually it's a typical summer afternoon that this happens, and you'll have gone through the what's called the boundary layer where it's all bumpy. All we can really do is to try and get a fairly even distribution of the nuclei through the bottom 800 to 1500 meters over the sea. And this is like putting cream in your coffee and giving it a stir. It's because of the turbulence that we can spread, not because of the initial velocity that we give the stuff. So it doesn't matter going out horizontally and then maybe even vertically a bit, sloping downwards, provided that later on you will be able to get into a bit of warm weather that wants to go up.
Stephen, I had a question about whether you follow. There's some other technologies that people are looking at to create little micro bubbles from the surface of the ocean that can be highly reflective. And apparently, they once created, they last. They can last several days. Much longer than one would expect. So, are you following that technology? Because your ships could combine. If there was a reasonably small sized device that didn't use too much energy to create these micro bubbles, you could consider putting those on your ships and spraying the air and also creating the micro bubbles in the wake of the ships.
The chap called Russell Seitz came up with this idea, and I'm in touch with him, and I promised that I will give him space on one of these if he can provide the goo that he wants to spray. I think the way to do it would be to have a pair of them that are moving side by side, maybe a kilometer apart, and you'd have a hose between them, which would be streamlined, and you'd have the bubbles coming out of the trailing edge of the hose. We want to spread them over a wide area, but we could certainly do that, and I would make sure that we can offer it to him. It will work much better, of course, when there aren't any clouds, and maybe ours will work better when there are clouds. Someone has claimed that it will actually work when in the blue sky, but only one paper's published about that. But
pulling the hose in the sky.
We could certainly drag hoses with spray generation.
What's his name? What's his last name? Russell Seitz.
Russell Seitz, and it's
S-I-T-E.
S-E-I-T-Z, and I think he's at MIT. It's either MIT or Harvard.
Okay.
I will send you his email address.
Yeah, that would be great. Thanks.
Could I raise a more general problem related to this of methods of geoengineering and marine cloud brightening as compared to other methods which have been proposed? Because not very long ago, I think we were all exposed to what I could only describe as a diatribe against geoengineering, where everybody who hates it got together and said it's foolish, it's preposterous, it's crazy.
That was absurd, eh, Peter? That was, what a joke that was. I mean,
yeah, it was. It was
really barking.
It was infuriating because it wasn't a discussion. It was one side of an argument.
Yeah, it was propaganda, really. I mean,
and the people who were saying that we mustn't interfere with God's will include this chap that we're showing now. In fact, his description of people who want to do a geoengineering, which is given here, is actually more like a description of himself, in fact.
And the picture complements it. But I mean, it's actually absurd, for example, that they cancel a simple project like the spice, right? They want to put a balloon up and spray, spray outside it. And, there's all this opposition. And yet forever, for 100+ years, we build huge smokestacks and power plants and scrape the surface of the earth and do whatever we want. And then some innocuous, very simple thing like just spraying something in the air. We do it on ski hills all the time. We make snow. I mean, nobody's up in arms about that. So it's really a completely bizarre, distorted argument against geoengineering. Like, it's just...
But it has
Stephen, this is the photo that you were showing before we started. And could you explain that? Because I think people would be interested in those colors that you're showing there.
Well, this one on the right is what Peter Wadhams will be interested in. And you can see that we are reducing the temperatures up here by maybe 4 degrees Kelvin, which is enough to do the job, I would hope. This is a result from some people in Norway. I don't know how to pronounce that, Stern or something, in 2018. But this is doing the cooling. Be warned a bit about this distortion of the Mercator projection. It looks as if it's cooling a very large fraction of that, but remember, it's round rather than rectangular. So that's cooling it, and it's fairly even cooling around here. And what's also a big relief is this one. We're looking at the precipitation, and the blue-green, to my shame, I've got the polarity that's wrong. That shouldn't be a minus sign. That should be a plus. We're increasing precipitation over Australia and the Middle East and the Sahara and South Africa and Mexico by up to 20%. Now, it's 20% from a rather low number, but this is what would be happening, only increasing the number of nuclei by 50%. It's really quite a gentle treatment in places just where there's clouds. Most of the computer modeling has said we'll spray everywhere between +40, -40 latitude all the time, but these guys just sprayed where there was a cloud in that computer modeling.
The advantage of this is one of the advantages of this method, I think, and where the hatred for geoengineering is, I think, because the only geoengineering that people think of is injecting aerosols into the stratosphere, where they stay around for a long time and may have unexpected effects. But marine cloud brightening is targeted. It's benign. It's only used at low level. It's targeted on where you want it to be applied. And if something goes wrong, you stop pumping immediately, and you're not doing any long-term damage.
3 days later, all forgiven you. This is from the Australian Bureau of Meteorology, relevant to what you're saying. And there's a thing called the Indian Ocean dipole, which is the temperature difference across the Indian Ocean from Africa to Indonesia and Australia. And if you have it cooler than normal, then you get less rain, maybe more bushfires in Australia, and you get more floods in Kenya. Okay. And what I would like to do is to have a fleet of spray vessels around here. They've all got email and sat-nav and stuff, and they're told whether to work here or here. And according to that, provided we can get the guys here and the guys here to agree with what they like, we can balance the floods and bushfires difference. And
it's controllable. The whole thing is
Yeah.
controllable, but with
It's like,
aerosols in the stratosphere, it's not controllable at all. They just
it's like having a steering wheel rather than locking steering on a car. And these actual things were happening at almost the same time, Kenya and Australia.
Yeah. Now,
this tells you how the intensity of hurricanes is affected by the sea surface temperature. Okay, from Whitney and Hobgood. Okay, so what we need to know is how much cooling would you need to do and where you want to do it in order to moderate hurricanes. And hurricanes actually start off, usually the ones that are affecting the Americans, over on the African side. This is how Harvey moved. Okay, and once you start things going, it's much harder to stop them. So what we'd want to do would be to measure the sea surface temperatures all across this one. Here we are. If we measure the sea surface temperature all the way around here, and we promised the people around here in
what is that? Sorry, that's a map?
that's Florida, okay, and here's South America.
Oh.
in
And
Africa, over
you're
on the
somewhere
other
up here,
Yeah.
that's Africa.
Okay.
And there's this is the water going off to the Arctic ice, okay, and this is the Gulf Stream, right? So what I'd like to do would be to have satellites measuring the temperatures around here, and these chaps saying we do not want 26.5 degrees because that'll give us hurricanes. We'd like you to put it down to 24.5, and we'll pay you according to how close you can get to 24.5. Now, nobody's brave enough to say, I promise you, you'll never have a hurricane anymore. We can't do that, especially if there's Americans who want to sue me. But we could say, it's so many million if we can get it by 3 degrees and so much for 2.5 degrees. And that's a commercial thing that could work, all right? And we would be cruising around here, adjusting the number of vessels, nipping off to the Arctic perhaps for a summertime, but we would control the temperatures all around the hurricane breeding ground, which is around here. Once you've started doing it, because there's a circulation, it's easier next year. It takes a while for coming around that loop. So you start off and you get the temperature pattern here to one that you'd like to have, or the countries around there would like to have. So that plus the Indian Ocean dipole, and wherever you do it, you're going to be reducing the deep temperature of the ocean. And that means that you'll be reducing sea level rise. And somewhere down here, I've got the numbers of spray vessels that you'd want to do different jobs. So we need 42 of them for 60 days to save the Arctic ice. Same sort of number to save the barrier reef. We need 400 of them to stop sea level if we did it over 20 years. And we need to do, Irma was going to be 160 vessels.
We see that those numbers are actually quite low.
Doable. Yeah.
So it's all doable, and in fact, you just enunciated a way in which you might be able to pay for marine cloud brightening by selling its services to hurricane protection.
Yeah.
Right.
Right. Yeah.
And there's another question that, just so it's on your radar for thinking about is, we're getting these incredibly scary droughts in the Western US, this year again as in other years. And have you thought of, I wonder if spray vessels off the west coast of the US could seed the air with, small particles that then the water goes to then to the trade winds the winds, of course, carry it across onto the land, right? And, maybe it's worth thinking about for, other applications for example, cutting into drought.
Well, the answer is yes, but I'm not sure quite where we would have to do it. But it may that the droughts we got in California now may have been originating in a hot blob that was a mysterious hot blob that was found off Alaska in the
Pacific
area.
Coast, yes.
A long
It's,
time ago. It was about
yes.
6 years ago. Now, if that was a source of heat there, whatever it was, that would be increasing the evaporation of seawater in that area. And that would be rising up with the warm air. And that would meaning that there'd be other air that had to be dragged in to replace it. And maybe the droughts we got now are because of that effect.
Well, it's the jet stream. I mean, what we're getting is huge ridges and troughs in the jet stream because of the overall warming of the Arctic, right?
Yeah.
And right now, the Western US is under this massive ridge, which is, so it's very hot and very dry. So if we can kind of figure out how the jet streams, you know, what is mostly, I mean, it's mostly the temperature difference between the equator and the pole, which drives the speed of the jet stream. And then there's topography and land-ocean contrast, et cetera, which sort of sets up these waves, these sort of quasi-resonances, you know, they're called. Like Stefan Ramsdorf and Michael Mann, there's some papers on that they've done on these resonances that are set up. And, you know, it's sort of, it would be interesting to actually see, you know, study, you know, placement of these ships to maybe reduce the amplitude of these wavy jet streams, right? That's something that people haven't looked at.
Jennifer Francis did a lot of work on the gradient between the equator and the Arctic. And she, I think she was, this is the way you might find out how to do it. Those are patterns of random changes into ups and downs, noughts and ones. Now, they're all different. They're all different patterns. And you could arrange in your computer model that these were whether you did or didn't spray. Okay. And if you did this and ran the computer model with all these different random sequences, you could then look at the results of the model and correlate them with these changes. And you should be able to pick up, if you have a long enough series, which might be 20 or 30 years of computer modeling, that's computer time, not real time, might be able to say this particular place does that to these other different places. And this would allow you to get an everywhere to everywhere transfer function of the effect of it. And this has been tried, and this is the sort of results we get. We were trying to find out what different bits of ocean do to a black place here. And this is saying that if you've got a red or a pink, it's making this bit wetter. And if it's a blue, it's making it drier. And this particular effect was the thing that was picked up by one of the very first climate models, where they said that if you sprayed there or here, you dry out the Amazon. But actually, most of the places here are making it maybe a little bit wetter. And if you do it here, up, down, in this place here, this is making this bit, this black bit here, be wetter. And this was done as one chapter of one PhD by a chap called Ben Parks at Leeds, supervised by Alan Gadian. And he had to make these lumpy changes. I'd like to see this replicated with much smoother changes for the areas where you did the spraying and the areas where you measured the results. But we could get an everywhere to everywhere transfer function, which will tell you exactly what you wanted to do using this pseudo-random method.
Well, some people who've said to me that this method won't work because it will take too long to determine whether anything is happening, whether any climate change is being affected by the spraying. But this sort of Morse code technique actually enables you to find out very quickly whether there are changes being correlated with what you're injecting. So it is a solution to skeptics about
the accuracy goes up with the square root of the time, and I think you'd want to run the effective time in the computer for about 20, maybe 30 years, but that's how long they do them anyway at the moment. But this is telling you everything about everywhere in one go. what's amazing is that I can't find any climate modelers who will replicate this. So all we got is one chapter of one PhD, admittedly by a rather good PhD student. But I cannot get them, and I can't find out why until I asked somebody who told me in confidence that the reason that they aren't doing it is they didn't know how to poke around inside the computer software. And they're probably not allowed to do it. So they're just, nearly all of them are just doing steady spray between plus or minus 45 or plus or minus 30 degrees, rain or shine, summer or winter. And that isn't the right way to use this technology.
If I can ask, related to the question that Paul raised about whether or not you can dump water where you want it on land as rain, I would have thought that some of the objections that the anti-geoengineering people would raise is that, you know, these clouds move around land and you're going to block the sunshine, and therefore there'd be less sunshine for raising agriculture. Do you have enough control over where these clouds are going to go to make sure you aren't doing that?
Let me show you this map here. Can you see that all right? The whole lot of people have tried to estimate how much salt is being thrown up by the wave action at sea. And what we've got is gigatons, that's 1,000 million tons a year. And what's happened here is that these guys who collected the information produce them, and what we've got here is a plot of them against the date in which the estimate was made. Okay, so the blue is the average of all these, and it must be a jolly difficult measurement to make, which is why there's so much scatter. But this is the best information we have. And if you look very carefully, you might see a black line along here from 1959 to 1960, and that is how much salt we put up if we were having 1,000 spray vessels working flat out all the time. So it is really very small.
Well, but in terms of simply reflecting sunshine, it would mean that there'd be less sunshine falling on your crops, and you know, maybe that's enough to slow your production.
There aren't very many crops over the sea. We're not affecting the numbers over land at all. At the moment, over the sea, there's maybe somewhere between 10 and 100 condensation nuclei. Over land, it's between 1,000 and 5,000. Okay, so what we're doing is completely ineffective over land because there's already so many aerosol particles. So we're only changing the sunshine over the sea.
Okay.
Is that when you say 1 to 10 over the sea? Is that per square meter or per cubic meter or?
Say again.
What when you say 1 to 10 cloud condensation nuclei over the sea, 1,000 to 5,000 over land, what units are you talking
about? They always
about?
measure it per cubic centimeter.
Per cubic centimeter. So that's particles.
So that's a cubic centimeter, and there's 1,000 aerosol particles in that cubic centimeter that I'm breathing in and out.
Gotcha. Yeah.
Okay. I mean, and I'm still alive, you know.
And if you're in a room with a smoker, then multiply by 100 or something.
Yeah, that's right. And it's between 1,000 and 5,000 in most bits over land.
Right. Okay.
I'm getting mindful about the time now, and we've got to close soon, but I want to get down to brass tacks. Looks like you've got a very ambitious project here that would take 50 years to build all these ships and do all the preliminary research and so on. If we speed it up, given the fact that this is supposedly a climate emergency, how fast could we get this thing into operation?
I think that if we really did it sensibly and intelligently, with some things being done in parallel with others, we could have the first one ready in 5 years. Okay, and we could make them in very large numbers in a hurry, because you can make them in lots of different places. So you could get all of them made in another few years after that.
Okay, and reduce that by a factor of 5 if we got Elon Musk involved, I think.
Yes.
It needs somebody with passion, well, because you've got passion, but passion and money to enact it, because you've shown us what needs to be done. We know what needs to be done. We just need the money to do it. And we are in a time, as Meta says, this is an emergency. And an emergency, when you're starting from scratch, is going to take a certain amount of time. Like supposing our only form of energy in the future would be nuclear fusion. You could say, well, this is an emergency, but it's still going to take us 20 years to get it going. But here there's an emergency and you know exactly what to do now. So there is the possibility, if the world became more sane, that you would be supported to do this at full speed, get this going in less than 5 years.
Well, yeah, but you're talking hypothetically about sensible politicians.
Okay, but the world becoming more sane is less of a probability than the world becoming hungry, right? I think the probability of the world becoming hungry and global famine within, say, 5 to 10 years is pretty high, actually.
Yeah.
The impetus of deploying this method to cool, will become vital, I think. And then,
well, yeah, I agree. But in fact, there's a paper came out just a week ago showing that the marine cloud brightening and stratospheric sulfur and cirrus cloud removal would increase food production by nearly 5%.
Yeah,
increase it by letting CO2 rise, which is very good for plants and vegetables. They like more CO2, but without having the temperature rising.
Mm-hmm.
So we would be helping the food, and 5% of food improvement is really very, very good to have.
It's huge. Yeah,
I'll give you the reference to that.
Yeah, definitely.
That's a point worth making to COP people who are resistant probably to any new thinking.
And the UN just has a new report that just came out yesterday on global drought. A whole 150, 200-page report on drought around the planet. And of course, it's very timely because we're seeing this massive, unprecedented drought in the US at the moment. All the reservoirs have dried up so much, in fact, that even the wildfire planes that they go into, they land in the reservoir. They don't land, but they scoop up water from reservoirs. They're saying it's too dangerous in many reservoirs because many rocks are now exposed. Mm-hmm. So they're extremely worried about the wildfires that are coming up in the US in the next few months. So
there's a paper by a chap in India called Bala, and he showed that there was a very small change in precipitation, but the river runoff increased with marine cloud brightening by 7% because of the cooling. If you warm the sea, it evaporates more, so you get more precipitation. If you cool it, you're controlling that. But also, if you make the drops of clouds in clouds over the sea be smaller, they don't rain over the sea, which means that there's more water left over when the air mass reaches land. So you have a way of controlling the strength of the monsoons. And I think you make the summer monsoons stronger and the winter monsoons weaker. But you have some control over it, and the small drops don't make rain, so you're making it rain somewhere else.
You're really inspiring me, thinking that now we're getting somewhere with being able to change hurricanes and monsoons and all of the all these other wonders. But let's hurry up about it. Our time is up, and
one final thing to say, which is that it's actually cheaper to do this than to have. If you can use the cost of corvettes in 1940 as an indication, it's actually cheaper than having climate conferences to do this.
Okay. Very good. Thank you so much. This has been extremely interesting, and I hope people take it and run with it. Let's get some action out of it. Thank you so much. Bye now.
Thank you.
Okay. Goodbye.